Okay, part 2 of 4.1 and 4.2 notes. All right, so another exponential function we have is an exponential function that has a base of e. Now, e is an irrational number, meaning it cannot be represented as a fraction. So if it's very similar to pi, which is a popular number that continues and is irrational, it would be e is 2.718281828, and like I said, it keeps going. So whenever you see this is also called the natural exponent function. It helps us model growth in nature. So we're going to do the same thing as we did above, except instead of b, we have a base of e. Okay, so what we're first going to do is, if we needed to evaluate e to the x at 3, you would plug this in your calculator, and you would get 20 point, and if I went to 4 decimal places, I'd have 0.0855. So if I wanted to graph this, then there's a couple specific points that I would graph. First things being first, I have an asymptote just like the other at y equals 0. So if I created my xy chart, at -1, I would have e, I'll write it down here, e to the -1, which we know is 1 over e. And then at 0, we still have 0, 1, because even e to the 0 is still 1. And then if we used 1, that would be e to the 1, which is e. Now, I understand you're not going to graph e, you're going to graph 2.7, blah, 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 blah. So go ahead and try to estimate those values now, and then you just graph them the best you can on your graph. And this is what my graph looked like. And again, something to note, or features to note, for this parent function is that it's a one-to-one function. The domain is all real numbers. We have a y-intercept of 0, 1, a range of 0 to infinity, and our asymptote at y equals 0, all like our previous parent functions. Okay, so now we're going to translate the parent function involving the base of e's. So the first thing that I'm going to do is write down our transformations that we used. So the first one that sticks out is this one right in front. And we know this as a vertical flip or reflection. Then up here in the exponent we have -2, so that means we go right 2. And then outside here we're going to go up 1. So the first thing I'm going to do is look at that vertical shift, because that is what affects my asymptote. So my asymptote is now at y equals 1. So it's important that we do our vertical flip first, because if you notice, this is where the majority of the graph is going to go, so it's going to affect our range in that case. So if you take this and plug this in your calculator, there are a couple specific points that you get that I'm going to plot. Okay, so I got the point 2, 0, and I got the point 3, -2. So I picked those points because when I plug them up here into the equation, so at 2, I'd have 2 minus 2, which would give me 0. Well, that's easy. E to the 0 is 1. So then I'd have -1 plus 1, which is 0. So that's fine. And our next one is 4. No, I didn't mean to plot 4. I meant to plot 3, so I apologize for that. 3, -2. And I chose this because if I did 3 minus 1, then I would have, 3 minus 2, I'd have e to the 1, which is 2.7, which therefore would be -2.7. So that means we plotted this point after we add 1 at -1.7. So this would be 3, negative 1.7 about, because again, we had to estimate the value of e. So knowing how it flips, my curve is going to look like this. Notice that it is a vertical flip of our e parent function, our base of e parent function. We went right 2 and we went up 1. The last part here that we need to denote is that the domain, like we know, is always all real numbers. But now my range is affected by going up 1 and this vertical flip. So now we're coming from negative infinity because of the vertical flip, and we're going to positive 1 because of the effect on the asymptote in our shift up, which again means that 1 has a parenthesis. So go ahead and try numbers 1 and 2 on your own and see if you get what I get for your parent function, your transformations, your graphs, and then your domain and your range. So this is what I got for my first one. My asymptote was affected by my down 1 shift, which also affected my range. I went left 2, and if I had to identify one point here, this one would be negative 2, 0. And then my parent function was y equals 2 to the x. And then for number 2, it was a horizontal flip because of this negative that was with x, which means it's a horizontal reflection. And then we also went up 2. Up 2 affected my range and my my horizontal asymptote, which is at y equals 2. So essentially, since we flipped it horizontally, we just took a growth problem and made it a decay problem. Okay, and the last part of exponentials is solving exponential equations using the uniqueness property. So basically, what we're going to do is try to create a base or both sides of the equal sign with a similar or the exact same base. So if you look at example number 1 here done for you, since they both have a base of 3, you can essentially let both of the exponents equal one another, which you see here. And then you simply subtract 4 to both sides, and you're left with x equals 2. Now, the next problem's not so easy because you have a base of 5 and a base of 25. Now, we can't change the 5 into anything else, but we can change the 25 into another number. And since on the left it's a base of 5, we want the right to also be a base of 5. So the left stays the same, and instead of writing 25, I'm going to write it in terms of a base of 5. So 5 to the what is 25? 2. So you write 5 squared, and then the x just hangs out. That doesn't go away. So the next step then is to apply the power-to-power property, which would make this 5 to the third equal to 5 to the 2 times x. And now that those bases are exactly the same, we can say that 3 equals 2x, and when you go to solve for x, you divide by 2, so x equals 3 divided by 2. Okay, so number 3 is very similar. That 3 can't be changed, but 81 can. So you're going to ask yourself, how can I make 81 a base of 3? So I can do that by saying 3 to the 4th. And then, like I said, over on the left, nothing changes. Well, this is simply just 3 to the 4th over here. No need for these parentheses, essentially, unlike the last one we just did. So we set the exponents equal to one another. 2x minus 1 equals 4. Add 1. 2x equals 5. Divide by 2. So x equals 5 halves. And our last problem over here. Oh, it's a little bit more complicated. So we don't want to keep it as 1/3. We want to make this into, think, a negative exponent. Okay? So what's another way I can write that and use 3 instead of 1/3? So that would be 3 to the negative 1, which is the same thing as 1/3. And then, how can I make 9 3? Well, that is 3 squared. So, again, this would be 3 to the negative 2x equal to 3 to the 2. Now watch this, parentheses x minus 6. Because this is a whole quantity, we're going to have to distribute. So we get negative 2x equal to 2 times x minus 6. And like I said, we need to distribute. And we get 2x minus 12. If you add 2x, subtract 2x to both sides, you get minus 4x equals negative 12. When you divide by negative 4, you get x equal to 3. So again, this is using the uniqueness property.